Hey YouTube, in my last video we discussed the natural exponential function f of x. Okay, so this f of x equals e to the x. In this video we're just going to kind of sketch a graph of what it might look like and just discuss a few of its basic properties and how it's related to, in general, any graph that is of the form like a to the x. It has many similar qualities. Okay, so let's go ahead and start by sketching a graph of this f of x equals e to the x, which I'm going to call this the parent function. Okay, but the best way to do this is actually start with a table of values. So we say like x, y, we say how about -2, -1, 0, 1, and 2. And so a few points I'm going to fill out first. First of all, I'm going to start with 0. If we took e to the 0, or anything to the 0 for that matter, you'd get 1 as an output. So this is kind of an important thing. This is our intercept right here. This is our y-intercept. When we plug in 0 for x, we get 1 for our output. If I plug in 1, we say we get e to the first. Okay, well, we know e to the first would be 2.718 to the first, which is 2.718. So this is roughly 2.718. So I'm going to write 2.72-ish. Okay, if we took e squared, well, now this is where I'd have to pull out the calculator and say, okay, well, I need e squared here. We'll take e power of 2. E to the power of 2 is about 7.39-ish. So we say 7.39-ish. So now when we go backwards, I do want to point this out. When we plug in a -1, we will get e to the -1, but this is the same thing as 1 over e to the +1, which is the same thing as 1 over 2.718-ish. So it should be a little bit smaller than, as a proper fraction. It would be smaller than 0. So here we go. We take a look at this. Oh, there went my calculator there. We say e power of 1 negative. And we get this 0.36, about 0.37-ish. So 0.37, and then we say, okay, same thing here. We have e power of 2 negative, about 0.14-ish, so 0.14-ish. So if I'm sketching this, what I want you to notice is, first of all, it is very similar looking to what a normal exponential function graph would look like. So in terms of points that we want to keep in mind, first one being this. Oops, didn't want to click on that. We'll click on my pen tool here. Click on this. It goes through the point 0, 1. Just like every other exponential graph, it goes through the point 0, 1, and this is our intercept. Okay. You'll notice this time, instead of a, we have the number e in for a, but that's about 2.718. So when we plugged in 1, we got the value of our base. So we said at 1, we're at a height of about 2.718, so it's about right here. And at 2, we were up here at about a height of, looks like 7.39. So let's see, 4, 5, 6, 7, 8, we're up here, okay? So we get this exponential growth looking thing on the right here. And on the left, we say at -1, we were at a height of about 0.37, not very high off the ground. And at -2, we were already at a height of 0.14. What this would indicate is that just like every other exponential function we've graphed in the past, it has this for an intercept. And also this, it has an asymptote that is on the y-axis. We'll switch over to like an orange here. It has an asymptote that is the y-axis. And so we say this asymptote has the equation y equals 0. Y equals 0, okay? And then last but not least, when we plugged in 1, we got the value of the base, 2.718. So here's what I wanted to do very briefly. Let's go ahead and take a look over this in a graphing program here. But you'll notice the things that I pointed out, that there's an asymptote on the x-axis. It has an intercept at 0, 1. This is our parent function. And when I plugged in 1, I got the value of my base, which is at a height of about 2.718. We can see all of those values reflected up here in the table, kind of that we had on the other page also. So what I want to do now is maybe sketch these transformations. So this first transformation here, we're going to sketch it by hand. And the second transformation here is a little bit more exotic. We're actually going to use a calculator to do it. But look at the first transformation here. I want to point a few things out. First of all, looks like we have an h value and a k value, which would indicate some sort of shift. Okay, so we'd say any exponential function with a natural base could be looked at this way: e to the power of x minus h, where h is our horizontal shift, and it's a liar. And we say k is on us. This is our vertical shift. So if I had to sketch a graph of this, I'd first start by sketching the parent function. So in this case, we'd say the parent function is this: y equals e to the x, which is what you see right here. If we were to now transform this to y equals 2 times e to the x, what this would mean is necessarily we'll take all our original y values here and we'll double them. Okay, so maybe we switch over to like a, I don't know, yellow. I never use like a yellowy color. Instead of 0, 1, we're now going to be at a height of 0, 2 on this graph. Okay, and instead of 1 comma 2.7, we'd be at a height of like 1 comma 2.7 double is about 5.4. Okay, and so this original height here, over here, it would be doubled, and so now it's clear up here, okay, up here somewhere. And so we've got the right side of our graph is very steep because of that 2. Also this, when we plugged in -1, we were at a height of 0.37 previously. Now we're at a height of like 0.6 something, okay? And we were at a height of 0.14 when we plugged in -2 for x. Now we're at a height of 0.28. So basically, we've stretched our graph here. So here, all we've done is graphed y equals 2 times e to the x. This time we're just going to shift it. We had an h value. If you look up here, h value of +2, which would indicate that everything shifts left 2, and then a k value of -3, which actually does indicate everything shifts down 3. So if I had to graph this again, maybe the first thing I would do is this. I'd say, well, our intercept here, which is at 0, 2 in this case, we're going to take it and we're going to shift it left 2, down 3. And so now it would be at this point here, here. We went left 2, down 3. I'm also going to grab one more point, which is this point 1 comma about 5.4-ish. And I'm going to shift it left 2, so at -1. And then instead of 5.4-ish, we're going down 3, so it would be 4.4-ish, 3.4-ish, 2.4-ish here. Okay, so now I probably should switch colors one last time. We'll go to like a fuchsia here. So we've shifted these 2 points, essentially left 2, down 3, left 2, down 3. And then now the only thing we have left to shift is this. If I shift something up or down, I'm going to shift my asymptote as well. So if this goes down 3, the asymptote should now be at -3. Recall that from a previous video, the horizontal asymptote shifts with the k value, so y equals k is the equation of our horizontal asymptote. But now graphing this, it would just look like this. So we sketched in the parent function, and then we applied this vertical stretch here, and then we shifted it where we needed to go, essentially. Okay. So this last one here, I wanted to use a calculator to graph this, but 5 e to the -0.17 t, okay, is our function. We can just head over to GeoGebra, but we'd say maybe g of x equals 5 times e to the power of, now in parentheses, -0.017 x, and we use x in place of t. So we would get, if I hit graph here, let me fix this a little bit. We get this function here, and I just want to make sure that I've got the right one. -0.17. Ah, that's why it's so flat. I'll fix my function here. It was negative 0.17 times x, and that'll make it a little bit better looking. See, we have this here. But a few things I'd want to point out. Basically, we usually have an intercept of 0, 1, 0, 1, okay? Here's the deal. Since I have a 5 out front, basically I'm taking that original 0, 1 and quintupling it. Now it's at 5, 0, 5. Also this, since we have a negative in front of our x, it's reflected about the y-axis, so we have exponential decay. And last but not least, we did not shift this up or down at all, so it has an asymptote that is still on the x-axis. But you know, these things tend to make sense when you think about them. So cheers.